Imagine a world of shapes and figures, a realm of lines, angles, and circles, each with its own story to tell, but without a common language to describe them. In this world, knowledge was scattered, fragmented, and often lost. Before Euclid, geometry was a fragmented collection of practical rules and isolated discoveries. Each culture had its own methods, its own way of understanding the shapes that surrounded them. Euclid's genius lay in organizing this wealth of information into a cohesive, logical system. He saw the potential for a unified approach, a way to bring all these disparate pieces together. He established a firm foundation from which all geometric truths could be logically derived. This was not just a collection of facts, but a structured framework that could be built upon. This was a revolutionary shift from knowing something was true to understanding why it must be true. It was a move from empirical observation to deductive reasoning. Euclid identified fundamental assumptions, his famous axioms, as the bedrock principles. These were simple, self-evident truths that formed the basis of his entire system. From these, he constructed the entire edifice of geometry with rigorous reasoning. Each step followed logically from the last, creating a chain of knowledge that was both strong and flexible. His systematic approach transformed geometry into a deductive science. It was no longer just about measuring land or constructing buildings. It was about understanding the very nature of space itself. Euclid's work became the cornerstone of mathematical education for over 2,000 years. His Elements was the primary textbook for teaching geometry, influencing countless generations of scholars. It wasn't just about lines and circles, it was about a way of thinking. Euclid's method taught students how to reason logically, how to build arguments step by step. The clarity and logical rigor he introduced were unparalleled. His work set a standard for precision and logical structure that is still admired today. He provided a universal language for describing and understanding space. This language transcended cultural and linguistic barriers, allowing scholars from different backgrounds to communicate and build upon each other's work. His vision truly shaped our understanding of the world. Euclid's contributions to geometry were not just about the shapes and figures themselves, but about the way we think about and interact with the world around us. Despite the impact of his work, little is known about Euclid's personal life. Most information comes from later commentators like Proclus, who placed Euclid in Alexandria during Ptolemy I's reign. Alexandria was a vibrant intellectual hub, home to the Great Library. Euclid's contribution was bringing unprecedented order and rigor to geometry. Anecdotes suggest a dedicated teacher committed to rigorous step-by-step learning. Euclid's Elements, a series of 13 books, is a masterful synthesis of geometric and number-theoretic knowledge. Its systematic presentation set the standard for logical rigor and deductive reasoning. Elements influenced Western thought, shaping arguments in philosophy, law, and science. The 13 books cover plane geometry, number theory, and solid geometry. Euclid's axiomatic method began with definitions, postulates, and common notions. From this foundation, he derived 465 propositions with meticulous logical steps. This rigorous system provided a blueprint for establishing mathematical knowledge with certainty. Elements became a universal model for rational discourse. Its influence extended far beyond mathematics. At the heart of Euclid's Elements are his 5 postulates, fundamental statements assumed true without proof. These postulates form the foundation of classical geometry, a system that has influenced mathematics for centuries. The first postulate, to draw a straight line from any point to any point. This simple yet profound idea allows us to connect any 2 points with a straight path, a concept that is essential in both theoretical and practical applications of geometry. The second, to produce a finite straight line continuously in a straight line. This means that a straight line segment can be extended indefinitely in either direction, a principle that underpins the infinite nature of lines in geometry. The third, to describe a circle with any center and distance. This postulate allows for the creation of circles with any given radius, a fundamental operation in geometric constructions and proofs. The fourth, all right angles are equal to one another. This axiom establishes the uniformity of right angles, ensuring that they are always 90 degrees, a critical aspect in the study of shapes and angles. The fifth postulate, more complex, deals with parallel lines. It states that if a line intersects 2 other lines and forms interior angles on the same side that sum to less than 2 right angles, those 2 lines, if extended indefinitely, will meet on that side. These axioms form the bedrock of Euclidean geometry. They provide the basic rules from which more complex geometric principles are derived. They establish the fundamental tools and concepts for geometric constructions. Without these axioms, the systematic study and application of geometry would not be possible. The axioms ensure consistency and uniformity in geometric reasoning. They provide a logical framework that mathematicians can rely on to prove new theorems and solve complex problems. They provide a standard for comparing shapes and proving congruency. This is crucial in many fields, from architecture to engineering, where precise measurements and consistent properties are essential. The fifth postulate became a subject of intense scrutiny, leading to new geometries. This scrutiny eventually gave rise to non-Euclidean geometries, which have expanded our understanding of space and the universe. Euclid's Elements builds a vast structure of geometric knowledge through propositions. Book 1 contains fundamental theorems like the pons asinorum and the sum of angles in a triangle. Proposition 147 is the Pythagorean theorem, rigorously proven within Euclid's system. The propositions form a logical chain, interconnected and building upon each other. The systematic construction of knowledge made Elements influential and enduring. It provided a model for building complex arguments from simple truths. Euclid's work remains a cornerstone of mathematical thought. The true revolution of Euclid's Elements lies in its method-deductive proof. This method was groundbreaking because it provided a systematic way to derive conclusions from a set of axioms or self-evident truths. Euclid insisted every statement be logically derived from established truths. This insistence on logical derivation ensured that each step in a proof was based on previously proven statements or axioms. This created a system of knowledge that was irrefutable based on reason. By building each new proposition on the foundation of earlier ones, Euclid's method ensured the stability and reliability of mathematical knowledge. A typical Euclidean proof follows a structured pattern, with each step justified. This structure not only made the proofs easier to follow, but also allowed others to verify the correctness of the arguments. This rigorous chain of reasoning demonstrates the truth of propositions. Each link in the chain is essential, and the removal of any link would break the logical flow, rendering the proof invalid. Euclid transformed mathematics into a deductive science, setting a standard for rigor. His approach was not just about solving problems, but about understanding the underlying principles that govern those problems. The method taught the world to think critically and argue coherently. It encouraged a mindset where claims had to be backed by logical reasoning and evidence. It provided a way to establish mathematical truths with certainty. This certainty was crucial for the development of other scientific disciplines that relied on precise and accurate mathematical foundations. The deductive method is transparent, allowing verification and reliable knowledge transmission. Anyone could follow the steps of a proof and understand the logical progression, making the knowledge accessible and verifiable. Euclid's approach influenced Western scientific and philosophical thought. His method of logical deduction became a cornerstone in the development of Western intellectual traditions. It remains a model for logical reasoning and proof. Even today, the principles of Euclidean geometry are taught as a fundamental part of mathematical education, underscoring the enduring legacy of Euclid's revolutionary method. Euclidean geometry has shaped the physical world in countless ways. Architecture relies on Euclidean concepts for design and construction. Engineering uses geometry for designing roads, bridges, and machines. Art has been influenced by Euclidean geometry for perspective and composition. Modern technologies like computer graphics and CAD software are built on Euclidean principles. Robotics and navigation also rely on geometric understanding. Euclidean geometry remains an indispensable tool for describing and interacting with our environment. Its principles are profoundly practical and continue to shape our world. Euclid's work is a testament to the enduring power of geometric reasoning. Euclid's legacy extends beyond the theorems and elements. His axiomatic deductive method became the standard for mathematical rigor. It influenced the structure of arguments in philosophy, law, and science. Euclid's Elements remained the authority on geometry for centuries. The fifth postulate, the parallel postulate, was less self-evident and led to new geometries. Mathematicians explored alternatives, leading to non-Euclidean geometries. These new geometries became essential in physics, particularly in Einstein's theory of general relativity. Euclid's framework inspired deeper insights into mathematics and the universe. His work provided the toolkit for rational inquiry and logical reasoning. Euclid's influence is a lasting echo in the development of mathematical thought. His vision continues to inspire exploration and discovery,